Okay. Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on Twitch. No engines, no libraries. We do absolutely everything ourselves. And that's both educational and for entertainment purposes, let's be honest. I kind of think it's fun. If you want to follow along with today's episode and you have pre-ordered the game on handmadehero.org using the little nifty pre-order button, you can download the source code, and be advised there are now two source code zip files. One for the first 100 days and one for that we're in currently. Make sure you download the latest one and unzip day 100 source code, because that's what we're using to start with here on day 100. So that's what you want to get on in terms of synchronizing with what I'm about to do, with what I am about to do. Now, we left off yesterday. We had basically finished everything, but we hadn't debugged it. So we're running and we're doing all the things roughly that we need to do, but we have some things that are either definitely or probably bugs. And so, like I kind of said at the end of last episode, I was like, all right, it's a little late now to start the debugging process. So tomorrow we'll just spend the time to step through and debug it. And if you remember, we had a couple different things that were bugs. First of all, we weren't transforming our normals, right? And so if things rotate, it's not correct. So we have to take a look at that. We were fairly certain when we were using the sphere normal map that it doesn't seem to be bending the correct way that we think it should. So we think we've probably got a little bit of a bug there. So we're getting close to having normal maps working properly. We just don't have sort of the fine details nailed down. So what I'd like to do first is let's just go ahead and start thinking about how we're going to fix this transform problem, since we're already set up to do it. We can see that we're rotating, and yet we're always still pointing essentially up and down as we rotate our bitmap, which is not at all what we actually wanted it to do. So if we come in to here, to our Emacs, I don't have an Emacs open, do I? No. It seems like I've got a lot of things open. Why are there so many things? Why do I have so many things open? All right. If I come over here to Emacs, and there we go, and I open up our renderer. So when we actually grab that normal out, right? We've done the work of grabbing that normal out, and what we want to do here is we want to be able to transform our normal. But we want to be able to rotate it. We've got it to do in here, rotate normals based on XY axis. We want to be able to spin it so that the normals are facing the correct way that they would be facing if the bitmap is being spun. Now, if the bitmap isn't spinning, it's no big deal, but because then the normals are all facing the correct direction. And so probably we'll want to have a fast path in here eventually, because there's a lot of things that we simply wouldn't need to do in all cases, because a lot of times we just have bitmaps that are that don't rotate, right? They're just in one stationary form without any rotation. So it's kind of a waste of time to do some of these things. But in order to support them all, we at least have to first make a path that does everything, and then we can sort of work on boiling that down into the cases that we actually need and can optimize. So if we want to rotate the normals, right? Where is the pen? That is a problem. I don't actually know where the pen is for our blackboard. There it is. It got slid up when we were when I was fussing with having to change the keyboard in the beginning of the stream. So if we go over to the blackboard for a second and just think about what this means, it's pretty straightforward. If we but we kind of just have to make sure that we work out the math right? It's a pretty straightforward thing that we're trying to do. Basically, all we're saying is that we've got a map, right? And in it, it's essentially got some vectors that are embedded in it, right? It's got information in there where there's vectors. And when we read those vectors out of the map, we're treating them as if they're as if the map was just right side up like this, right? And so we have, an X and a Y axis or something like that. Here's our Y axis, here's our X axis. We have this X and Y axis, and even if those axes end up being rotated, as like so, right? We are still grabbing, when we grab this out, right? The texels in here still have the same direction. So when we grab out this texel, it's still going to be pointing like that, even though we've rotated like 45 degrees, and it should have been pointing like that, right? And so what we need to do is we need to use these axes to rotate our normals as well. Now, if we're doing non-uniform scaling, right, meaning the x and the y are going to get scaled non-uniformly, which we're currently allowing, this gets a little bit hairy. And the reason it gets a little bit hairy is because you have to sort of consider what actually happens with normals in that case, right? Like, you know, if you imagine that this is a vector that goes between two things, if I was to scale up the y, right, you kind of have to imagine that the normal there is going to stretch kind of like this, right? You know, like it's going to end up being, well, I guess if I was to draw it exactly correctly, it'd be something like this. If I was to scale up the y-axis, right, my normal is going to scale up in that fashion, just as if it were kind of a point that was being scaled up, right? And the question is that actually what we would want to happen if we took the surface that was being represented here and did a similar scale, right? And so what I want to sort of draw for you first is just to sort of, you know, if I can get you thinking about this, let's say. So pretend we have, let's pretend we have something that's maybe like a shape that looks kind of like this. Maybe it's the edge of like a gem or something like that, right? And so, you know, the normal is pointing, let's say, at a kind of a 45-degree angle here, right? The normal is pointing off like that, okay? And what I want to show you here is that if I were to take the y-axis, right? If I were to take the y-axis and scale the y-axis up, right? So if I were to increase that, then the shape that the normals are coming from, that the normals are supposed to be representing, is going to elongate, right? So I'm basically going to get something that looks like this, right? I'm going to get, well, it's going to shear, essentially. So it's going to be like, I can draw a little bit better version here, right? So, you know, imagine this is getting scaled up a bit, and, you know, so it's going to elongate this piece here as the whole thing scales up, right? Well, if I was to scale the normals by that same amount, right, you can actually see that what'll happen is the normal will also scale in that same way if I was to use the same axes, right? But if you look at what the surface did, really the surface is implying a normal that would do the opposite thing as that, right? Meaning the normal to this surface will actually point this way more. It'll actually point more down this way as this surface elongates. So really, if we are to support non-uniform scaling, if we actually want to do the normals correct, it's not simply the case that we can just scale our normals by the same thing as we scale our regular images by, right? And that's because, you know, this is one of those places where if you happen to have a lot of linear algebra knowledge, it's helpful because this would be obvious to you. But if you don't, it's not. And so I'll try to kind of give a little bit of the background here. Again, not a mathematician, so I can't give you kind of the full deal, but I can sort of give you a window into what's going on here, right? So the deal is that actually vectors are not all the same, okay? And there's a lot of reasons why vectors might not be the same. Obviously, you know, you could think of things like, okay, well, if I have an RGB color value, or let me give you a more specific example. If I have an RGBA color value, right, and this is pre-multiplied alpha, you've already seen that it operates differently than if I had an RGBA thing and it was non-pre-multiplied, right? We know that this one will allow us to do linear operations on and it works, whereas this one, it doesn't, right? And so we've kind of already seen that vectors are a way of bundling numbers together at their most fundamental level. We treat them as sort of a way of working on numbers together, but that's a very mechanical notion of vector, which is not the same as the theoretical notion of a vector that might exist depending on what kind of operations you're doing, and we kind of can see that difference here. Like pre-multiplied alpha is a proper linear, conceptually linear vector that does the things that we might want it to do, and non-pre-multiplied alpha is not that way. It's a different thing. It's sort of a different object in a sense, mathematical object, not programming object. And so you really do have to understand that vectors behave differently, and in this case, that's sort of what we have. The points that make up this shape are one kind of vector, or one kind of point, you might say, but one kind of vector that goes from the origin to that point, right? That's one kind of vector, and behaves one way when the coordinate system changes. But these normals are a different type of vector, and there's actually terms for this. I believe they're covariant, and I want to say contravariant. Is that right? Covariant, contravariant. I don't really remember the exact terminology, so I'm not going to write it on the blackboard. I don't want to be wrong. But basically, there's different types of vectors when you talk about having a transform that you're passing them through. And so if I have some transform, like we have this elongation, we'll call that f, right? When I put one of our points through this f and we get out a new point, right? If I want our normals to come out so that they obey the same properties that the normals want to obey, it's not the same transform, right? It's not x anymore. It's actually a different transform that you would have to push the normals through. Now, again, if I remember correctly, what happens, and you know what we should do? We should ask pseudonym 73 for these terms. He will know these terms for sure. They're very standard linear algebra math terms, and it's just been so long. I used to know them even. That's how common linear algebra they were, as I used to know them. But I've long since forgotten. But basically, normals and the points in the plane are treated differently. And you actually see this in linear algebra. You see it actually written differently even. Whereas you will often see vectors that are these like sort of point-like things, they are often written as column vectors. So you might have px, py, pz, right? But normals are not. Normals are actually written this way. They're written as row vectors, right? They're actually not even the same shape in the math. They are transposed as compared to these guys. And the rule for how covariant, or well, I guess I don't even want to use the term, how normals are transformed is that if you have a transform that operates on your points, there's actually something called the inverse transpose that operates on your normals. And in order to sort of get into how this actually works, we'll probably have to open up matrices a little. And I don't know if this is a good idea for today. It seems like we may be going down a little bit of a math hole. But sometimes you have to go down the math hole. So maybe we'll introduce this concept and we'll think about it a little bit. Okay. So what was I doing before, right, in terms of constructing these p vectors, right? Well, we had stuff that was in 2D, right? So I had a px and a py, right? These were points in space. And what I wanted to do was I wanted to start treating these points as if they were in some coordinate system, right? And so what we did is we constructed a thing where we would say, okay, the point that we actually want on the screen, right? Or I guess we could call this the screen space point or something, right? What we ended up doing is we took the two components of this thing that we were describing, and we would multiply them by like an x-axis vector and a y-axis vector. And remember, this was our coordinate system test thing that we made, where these are, they vary, right? These two things are vectors, 2D vectors, that vary, and they were what allowed us to do like rotation stuff. We would rotate these vectors, and then all of the point values would correspondingly move with them, right? Remember we had that little grid that was moving around and everything? And we could scale it, we could rotate it, and that was the basis that formed the basis both literally and figuratively of what we were doing with getting rotation and scaling to work for our texture mapping, okay? Well, we can actually write this in matrix form, and we haven't really done much with matrices yet, but now might be a reasonable time to do that. And so if we think about writing this in matrix form, we have to just kind of go back and review how matrix multiplication works so that we're all on the same page there. Because we haven't done it very much, and I don't want to spring that on you without giving you a little bit of a background on it. So let's say I have a matrix that is, a 2 by 2 matrix. And matrices and vectors are basically cut from the same cloth, right? They are arrays. If you're a programmer, you can think of them as arrays of numbers that go together, right? And so if I have a vector here, and I have a matrix, well, you remember how we did one extremely similar example to this when we did the dot product, right? When we did the dot product, we had something where we did like one xy and one, we did one vector times another vector, and we did the dot product, right? And we said that was whatever this vector is. I guess I don't know. We'll call that v0, and we'll call this v1, right? We said that was v0 transpose v1, right? In fact, let me just do this here. v0 transpose v1, right? And we wrote it that way for our dot product. And remember, we wrote it that way because we were turning this vector on its side. And that's what the transpose operator does, right? It turns things on their side. And we're going to see that a little bit more explicitly, what that means for bigger shapes than just vectors in a second here. But that's how we wrote it. And then when we did our multiplication, remember, all we had to do was just go, okay, we just add the terms and we line up multiplication, right? So we start with the first one in each, we multiply to get ax, and then we add. We start with the next one down, we multiply, and then we add. And we would just keep going no matter how long the vectors are, and that's what produces that dot product. Well, a matrix multiply is no different, right? Or I should say a matrix times a vector multiply is no different. But really none of these are different. Matrix times matrix would be no different either. All you do is you start with the column and the row, the first column and the row, and you do that dot product. You take the first term, right, and you multiply them together. You take the next term, you multiply them together and add, right? And you would keep going if you had more. When you're done with that, you go on to the next one, right? Next row, column. So it's cx plus dy, right? So really what we have here is two dot products, right? We have two dot products. We have this dotted with this, and we have this dotted with that, okay? Now, you may ask, well, I don't understand why you're telling us that, because this is not dot products. What are you doing? Like, how are these related? I don't understand, right? And that's true. It's a little opaque what's happening here, and that's because this is just one way of breaking up the terms. You can see those dot products there, right? And this is the conceptualization if you were thinking about it in terms of dot products or inner products, right? These are the same thing, same term, right? So this is the inner product view. But there's another way to look at this, right? Because if you take a look at what's happening here, right, you can actually see that there's another way we could break up what's going on in this particular equation, right? Because if you sliced it this way instead, right, you could imagine this as being the sum of two different vectors, right? This is also, you're just reading it off, the sum of ax cx, right, plus by dy. Do you see how I did that? I just grabbed these and I grabbed these and I broke them out into two vectors, right? This, if we added them together, would also produce the same thing, right? So this product that we did just by using the matrix multiplication rules, we can also see it would work the same way here. And what we also see is each of these vectors has a common term in them. So if we wanted to factor it further, we could say this was xac, right, plus y bd, right, by just pulling that out. Because remember, scalars multiply into a vector. They just multiply straight on in there, right? So this is actually another way of looking at this matrix multiplication, which means that this, if you imagined this was an x-axis here, and this was a y-axis here, right? It essentially means that the columns of this matrix are the axes, right, of our transform format that we have been using. So we could, just trivially if we wanted to, start thinking in terms of matrices just purely by packing our x and y axis into a matrix. All we would do is create the matrix that has our x-axis is x at the top, our x-axis is y at the bottom, our y-axis is x in the next column over, and our y-axis is y underneath. This is the fundamental transform for rotation and scaling for 2D. That's what it is, right? That's what that allows us to do. And so here's our x-axis, here's our y-axis, here's our matrix. Okay? And so really this whole time we have been doing matrix math by writing this manually. But we didn't have to. We could have been doing it in matrix form if we wanted to. Now, you may ask, why would we do it in matrix form? And the reason is because if you start thinking about this in terms of matrix form, where I just say, okay, I've got a matrix and here it is, you can actually start writing matrix math, which is much like what we did with vectors. We could have done all of the work that we did with vectors in scalar, but we chose not to because once we elevate up to vectors, it's much easier for us to build up sort of a grammar of what we are saying we want to do that just operates on the vectors. And that allows us to break free from having to micromanage all of these scalar quantities. And the same thing is true of matrices, right? That's exactly the same thing that happens with matrices. We can build up the transforms. For example, there is operations which multiply matrices together. So if we were to have one set of rotation and scaling that we wanted to represent, and we did it this way, if we then made another one, right? So we've got another one here that's got some, I'll just put dot, dot, dot there, that's got some other set of axes. If we wanted to know what A's coordinate system would look like transformed by B, we can actually just make another matrix, which is these two multiplied together. And then this one will represent the combined transform without having to store any more numbers. It still only stores a 2 by 2, but it encapsulates everything that was happening with these two matrices. Furthermore, matrices, in addition to having multiplication, they also have inverse. If I wanted to say the opposite of the transform that happens with A, I can do A inverse. And they also have, you know, other things like addition and so on, but we probably won't really be able to do much with those. Those are usually more for numerical solving and stuff like that. Inversion is something that's pretty tricky. We'll talk about that in a second. But if you take a look at matrix multiplication, that is actually trivial. I've already taught you how to do it. All you do is literally do the exact same thing I just sort of harped on up here. This process, if you do that, is exactly the same with matrices. If I was to say have A, B, C, D, and then I wanted another matrix here, which is just going to be U, V, W, Y or something. I don't even know why I picked those. You do exactly the same thing. And you know what I might do? I might spread this out a little bit just to make it a little easier for us to see it. So let's call that UV WX, let's say. All right, there we go. So if we were to do this, again, you are trying to form 4 different products because you know, and I guess I haven't mentioned this yet, but whenever you do matrix multiplication and you line them up like this, you get as many rows as you have on the first term side and as many columns as you have on the second term side because you just line them up like this and you can actually see right where they go, right? When you do that multiplication, you can really just do it mechanically. When you want to solve for one of the terms, you know you're going to have a 2 by 2. When you want to know what that term is, you just read it off. You take the terms, right? AU plus BW, right? That's my first term. Just that straight dot product, exactly how I would do it. You want to do the next one, same exact thing. A and V, X and B, right? Go down to the next row, same thing. UW and CD, no problem. CU plus WD. You want to do the final one here, no problem. CV plus DX, right? And that's how you do matrix multiplication. There's literally nothing to it. It's just a series of these dot products, which you could do totally by rote, nothing fancy. So if you just write it in this tabular form, it's pretty easy to see exactly how it works. And that is all you need to start compositing transforms. Now, we don't have a lot of need to composite transforms, which is why I haven't done any of this yet, because we really just don't have a lot to do with that. But now, when we're sort of talking about these covariant the different types of vectors and stuff and how they transform, it becomes handy to start talking about it in a more linear algebra sense. And the reason for that is just because a lot of these things become clearer if you can start talking about something as the inverse, and we all know what that actually means conceptually, rather than having to sort of go through and derive it. So if we actually want to talk about the 2 operations that I mentioned, so we have 2 operations, A transpose, right? And we have A inverse. So we have, this is the inverse, and this is the transpose. Now you've already seen what the transpose does. It lays things on its side, right? We did that here. right? So here's what the transpose does. The transpose lays things on its side. Well, what does that mean for a matrix? Well, actually, what it's really doing is it's actually sort of doing a mirror around the diagonal. So the transpose as an operation is a thing where if you have this, right, and you want to transpose it, what you actually end up with is you draw that diagonal. You imagine that diagonal going straight down the matrix, 0, 0, 1, 1, 2, 2, and so on for the coordinates in the matrix, right? You leave that untouched because everything flips around it. But all other things, they exchange around the diagonal. They mirror. So the B would come down here and the C would go there, right? They would flip. That's the transpose. And that's true no matter how big this matrix got. If I had more values here, right? So if I had stuff like this, basically these two would have exchanged, these two would have exchanged, just like these two did. And you can keep going. It doesn't matter how big it is. However big the matrix is, you still are doing that exact same thing. Everything on the side of that diagonal, it flips, right? So every single thing flips, right? That's the transpose operator. Very, very simple to understand. We'll get to why it's important in a second, but it's extremely easy to produce because in some sense you don't even really need to do anything. It's literally just a reordering of the things in the matrix. And oftentimes you actually do the reordering because you're trying to make it flow through properly, but you could almost imagine swizzling the indices on a matrix would be, one way to do a transpose on it. You could almost just have a flag that swizzled the indices. That would do it. If for some reason it was expensive because they were big matrices or something, right? So that's how transpose works. Now, inverse, on the other hand, is more complicated. If you have the inverse of a matrix, the inverse of a matrix is defined as whatever the matrix, it's times, in fact, I guess I could draw this out a little bit bigger. So if I have a matrix here, like so, the inverse is defined as the matrix where if I was to multiply it by the original matrix, right, I would get 1s in the diagonal and 0s elsewhere, okay? And this is a special matrix which is actually usually called the identity matrix, right? The identity matrix is the one that does absolutely nothing to the things that come into it, right? And you can see why that would be. If you imagine multiplying a vector by one of these guys, right? You can see what happens when we actually do the math that I was saying. In comes the vector. It's going to multiply xy times 1, 0. Well, that's just going to pick out the x coordinate, right? And the y is going to get multiplied to 0, so there's no additional term. Same thing if we do the math here, right? It's going to the x is going to drop out. It's going to be multiplied by 0, and the y is going to be right there, right? So we end up with just getting the same thing in as out. And the same thing would be true if we stacked a matrix up here. We get the same thing. So an identity matrix is just something that does literally nothing. It's completely inert. It has no effect on anything that multiplies by it. Now, technically, this is the multiplicative identity, right? And furthermore, it's the multiplicative identity on the right. Because technically we're multiplying it on the right side of this term. If this was A and this was A inverse, we're talking about the one that comes on the right. Now, that's not something you really have to think about in anything that we're going to do, but technically there's left and right inverses in matrices when you start getting into matrices that are not in the same kinds as we're doing. So I'm not even going to touch that. But suffice to say, technically, this is like, I don't know if this is the right term for it, but these are the properties. It's the multiplicative identity, and it's the one on the right. But furthermore, the reason that I said that multiplicative identity is because it's a multiply. It's saying it's the identity in terms of multiplication. You could imagine the additive, right, identity. The additive identity would not be that. If I was going to add matrices together, adding matrices is exactly the same as you do with vectors. You just add each component, right? If I was to add, I would end up with A plus 1, B, C, D plus 1, which is not the same matrix, right? So the additive identity is just all zeros, is a matrix with all zeros, right? And that's the same on the right or the left, but that's a separate issue, right? So again, additive identity, none of this stuff we care about at all. I'm just pointing it out so that if you want to go read linear algebra, you're not totally left in the dark. And we'll get back to the stuff that we actually care about. So the inverse is the matrix that would go here such that we could produce the identity, right? And so if you think about it, we know what this matrix multiplied out to be, right? We produced it here, right? Here's what it is. And so we can think about how we would get an identity matrix out of this, how would we make these u, v, w, and x? What would we make those values if we wanted this to come out to be equals 1, equals 0, equals 1, equals 0, equals 1? Well, the answer, obviously, is you've got a system of 4 equations and 4 unknowns. You could just solve them, right? We don't know u, v, or w, or x. We do know a, b, c, and d, and we know 4 equations using u, v, w, and x. So all we would have to do to produce the identity is solve the 4 equations, and that would produce what we want, right? Now, that's a pain in the butt. I'm sure everyone thinks it's a pain in the butt, because honestly, as soon as I see something like solve 4 simultaneous equations, I'm like, hells no, right? Because I don't even want to go down that route, right? I don't want to solve 2 simultaneous equations, let alone 4. It's just an invitation for me to make careless errors in the math, right? But fortunately, I feel like that is where Gauss steps in, right? And Gauss, who is also known as, like, arguably greatest mathematician of all time. I don't know if pseudonym 73 wants to step in here and comment on that, but just in terms of sheer quantity of stuff that the dude figured out by himself, I feel like he's probably that guy. There might be 1 or 2 other people who could be competitors, but like Gauss is pretty insane. And like I said, I think on an earlier stream, he even invented stuff that other people have their names on. Like the Fourier transform, I think, was actually him. He just didn't publish it or something, but he actually got it first, right? So it would be called the Gauss transform if he had bothered to like put it out there, right? So he's crazy. But point being, he didn't want to do this either, because he was just like, why am I going through all these steps? There's got to be a better way. At least I'm putting words in his mouth. He probably didn't say anything like that, honestly. But point being, we have a thing called Gaussian elimination, which actually is a pretty easy way to deal with situations like this where you want to solve equations and invert matrices and that sort of stuff. This is actually a pretty easy way to produce those inverses when you have small matrices and you're not super worried about a lot of numerical finickiness. Now, Gaussian elimination is not something that you actually use to invert or solve large matrix systems. In the real world, where the matrices are huge, I mean, a lot of times scientific computing, you're talking about matrices with hundreds or thousands or tens of thousands or millions even, if you're really unlucky, of elements. And there's just that's not on the table. Gaussian elimination, I believe, is an ON cubed algorithm, so I'm pretty sure you're not going to run that on anything large. So they use other things, and furthermore, it's numerically unstable in a lot of situations, so there's other things that are better for when you're dealing with floating point numbers and that sort of stuff. So this is not a power tool that you would be using if you really cared about matrix math, but we don't actually. We're talking about very simple things, very simplistic 2x2 matrices that are well formed. They don't require any special handling. And so if we want to think through how we can solve one, we can actually use Gaussian elimination fairly easier. So what is Gaussian elimination? Well, it turns out that matrices, well, surprise, surprise, matrices actually weren't invented for computer graphics. I know it's shocking, but they actually weren't. They were actually invented to solve systems of equations. That's what they actually were. So typically what you do when, the reason that people created matrix math in the first place is they had a lot of stuff that looked like this. They were like, well, I've got, some stuff that looks like that. EX plus FY plus GZ, ... And they would just have these systems of equations where they just had tons of tons of equations and tons of unknowns, and they're like, you know what, this is all, the process of solving these is all very mechanical, and we're doing the same thing every time. We should come up with a more straightforward tabular way of solving these that's more regular. And when I say they, I guess I should say Gauss, because I guess he's the one who invented it. And what they realized was, well, if you've got equations, right, and you've got, these sort of common, you've got them all in a bunch of unknowns that you're trying to solve for and whatever, you can actually put them into a matrix. Just put the coefficients into a matrix, right? A, B, C, E, F, G, H, I, J. Don't know why we skipped D there, but we did. You can actually just put those into a matrix and consider the matrix to be the coefficients of the equations that you're looking at. And there's some other steps that you would go through here. Normally you do a thing where you've got, you've got this. You would put x, y, and z into a vector of unknowns, and you would say, okay, we've got some product here, and then we've got equals whatever was on the other side of this equation would be out here in something called a b vector, and you'd end up with something called ax equals b, which is the standard matrix problem. We don't care about that at all right now. I'm skipping it. Point being, what happens here is if you think about the way that you actually would solve equations in multiple unknowns. So let's say that we just had A, B, C, E, F, G, H, I, J here, and we were working with those, right? So what we wanted to do is we wanted to start solving for these. Well, what you do is you first try to knock out terms, right? You know how you do this when you solve, right? You start eliminating terms so you get down to one term, which is like, this last term equals something. You then divide by the coefficient and you get z equals something. You can then plug z back into other things and you can back solve for each thing going upwards and so on. So what they did is they sort of regularized that process. What they realized is that, well, since any equations, right, any equations that we have, we know that if we take, and this, I guess for people who are not familiar with math, I guess I'm blowing through so much math. This is turning into just a giant math episode. Sometimes that happens on Handmade Hero. Sometimes it happens. Sometimes you end up going down the math hole and you're just in the math hole. So I'm sorry, that's where it's at. We're just in the math hole today. Nothing else is going to happen. We're just entirely in the math hole. All right, so in the math hole, so if you, what was I about to say? Applying these things into the matrix. I totally lost my train of thought by thinking about the math hole. I don't even, yeah, it's a strange term. I like it. Excuse me, but it's a bit weird. All right, I don't know what I was going to say, so I'm just going to skip it and go back to talking about what I was talking about, and presumably I'll just end up saying it again when I come to that point again. All right. So anyway, what they realized is, all right, if we are to build one of these things, right? If we're to build sort of the matrix out of just the coefficients of the unknown that are on the unknowns that we wanted to solve for, what we could do is we can, that's what I was about to say. I knew I would get to it because I have to describe it. I'm like, I wouldn't be describing it if it wasn't a prerequisite for what we're about to do. So if you have two equations, right? If you have an equation, here's the left-hand side of an equation and here's the right-hand side, right? And these are whatever you want. All I know is it's an equation. Well, if I have one equation and I have a second equation, right? What I know is I know that these two terms are equal and that these two terms are equal. So if I wanted to, it's totally legal for me to just add these two things together, right? I mean, I can just add anything I want to both sides of an equation as long as I add the same thing to both sides. So since I know these are the same thing, they're equal, I can just add, right, LHS2 and I can add RHS2. Because I know that LHS2 and RHS2 are the same value. They're equal, right? So what this means is you can add any two equations, right? For free, right? Yes, you can. Totally fine. You didn't violate anything by doing that. You can do that all day long. Furthermore, you can multiply these by anything you want, right? If I was to say add 2 LHS and 2 RHS to both sides, totally legal too, right? Because as long as I multiply them by the same value, they're still the same value on either side, right? I'm still adding the same amount to both sides. So since I can do that, what they were saying is, well, okay, now that we've tabulated these, what we can do is just think in terms of operations on the rows and columns of this matrix, right? And we can regularize it, right? So what we can do is we can say, oh, okay, right? If I take this top row here, right? I take this ABC row, and what I want to do is start knocking out this bottom row, like the HIJ, right? What I can do is say, well, if I wanted to eliminate H, all I would have to do is say, well, what is H divided by A, right? what is the amount of A I would have to add to get me to get it to be equal to H, right? I'm not sure I'm explaining this in a particularly good way. You know what? Let me do it with a number so you can see, because otherwise it might be a little. Pretend we're not talking about letters right now. Let's just say we were talking about numbers, right? So I've got 5, 2, 3, 1, 7, 6, and then like 10, 4, 9, right? And I want to knock out values here. I want to eliminate, right? Essentially eliminate terms, right? So I want to eliminate this term. So what I can do is I can say, well, how many of A would I have to add to this, right? H over A tells me how much I would have to add of A to knock out, if I was subtracting it, to knock out the 10, right? And in this case, you can see that that would be 2, right? So what I can do is I can take this row, multiply it by 2, and subtract it from this row, right? So that would give me 10, 4, 6, right? And now I can subtract it from here, and that totally eliminates this, this term. It actually happens to also eliminate this term. I didn't actually mean to do that, but that's what happened, right? So then, instead of this row, I would now have a 0, right? I would have another 0, and then I would have a 3, right? So now I have accidentally eliminated 2 terms. I only meant to eliminate 1 term, my bad. But now I've eliminated two of the 3 terms, and now I have just 1 term left, and that would correspond, right, to just having like this Jay-Z term here, right? I don't know, Jay-Z's a rapper, I believe, but this is not his term. This is our term. So anyway, if you are to do this process, you can then divide this last remaining term, the 3, right? And instead of actually bothering to eliminate it, or I could actually go ahead and actually eliminate it by using one of my other things, but that's not that's not productive, right? Because I don't know if you can see how this would work here, but if I was actually to do that, it would be hard for me to eliminate this without adding in quantities to these things here, right? So 6 of one, half dozen of the other. But point being, once you've eliminated things, you can then divide this by whatever the target is that you were working with over here, and you can eventually produce what you want to end up producing is that identity matrix, right? Now there's more steps involved here, so I kind of have to go a little bit deeper, but I just want to make sure you understand this one process right here, which is the ability to add rows to other rows, right? The ability to sort of say, I'm taking one of the rows of the matrix and adding it multiplied by something, or I should say subtracting, or multiplying by a negative and then adding, whichever way you want to think of it. I'm basically using a row of the matrix to eliminate members of another row of the matrix, right? Okay, so that's kind of very handy, and what you can sort of see shaping up here is this is much more computer friendly, right? Like, thinking about how to solve linear equations, thinking about how to solve this may be a little confusing as to how do I have a computer do this? Do I have to start making like a symbolic algebra thing or something like that? But this is a bag of numbers, and that operation is something we could all write very easily, right? So you can start to see why it might be possible to program something like Gaussian elimination into the computer. All right, so let's take it a little bit one step further and talk about a little bit more explicitly how this would work, right? So what we want to see, right, what we want to actually have here, as I was saying before, is we have A, B, C, D, right? And we want to produce something which, when we multiply it together, right, we're going to end up with this, right? So we want like something up here, and we want to produce this, you know, this matrix, right? So we want to be able to multiply by terms that are going to result in us getting a 1, 0, 0, 1, right? Excuse me. So another way that we could think about this, I'm trying to think if there's a good, man, it's been a long time since I've done this. I feel like there's a good way to motivate, you can actually do a very simple trick here that makes it a lot easier to conceptualize how to do Gaussian elimination to produce the inverse. Basically, you do the Gaussian elimination on this, but I'm trying to think of how I would explain why that works. It's been a long time since well, I'll just explain out the full thing, and then we can see if I can think of the other way, the simple way to do it. Maybe I can go look in a book tonight or something and show it on tomorrow's stream. So anyway, point being, so we got two things here. In fact, you know what I'll do? We won't even talk about the inverse yet, because maybe I can go look up what that nice trick is, and that'll be an easier way to sort of explain it more easily. Let me talk about the regular solution form first, right? So the thing we were talking about before, we'll just make it absolutely explicit. So we know what this produces, right? We know that this produces this, right? We know that that's what that multiplies out to. And here we go. Let's say, right, that we have some values that we want here, right? So let's say, because here's a system, right? We know that this is how we would do this multiplication of vector times matrix, right? That's what we're doing, vector times matrix. We know what it would produce. We would know how to do it forward if we had to do it forward. Meaning if I gave you this matrix, if I gave you a matrix A, and I gave you a vector, we'll call the vector x, even though I already put an x in there, that was probably unwise. And we'll call this b, right? If I wanted you to produce the quantity ax, I showed you how to do that. If you know what x is, right? You know that you just multiply it like so, and here's the result, right? This is ax, right? We've done that. But the question now, and the place where all this elimination and such and so forth comes in, is what would happen if you didn't know these? So that's the case that we're talking about here. You have the coefficients of your matrix, but you don't know what these values are, and you want to solve for them. So I have some uv over here. I have some values. I know b, right? Let's say I know the result. So instead of trying to find this result, I know the result. I know what this evaluates to. What I don't know is what are the values I would plug in to make that happen. It's the classic solve. So this would be a solution of two equations and two unknowns, right? And so that is where we kind of get into, that is where we get in to how we could do the Gaussian elimination. Again, remember, these are just equations, right? So if I want to, I can just write this and say, okay, this is just my a, b, c, d, right? My x, y equals uv, right? That's all we're doing here. And if I want, I can actually do the Gaussian elimination on the entire thing at once, right? Because again, these are just equations. You can think of these as two different equations written in two rows, right? So if I want to, I can just go ahead and straight up do the first step of the Gaussian elimination, right? I can say I've got my A, I've got my C. I want to knock out that C so that I can solve for Y, right? And so if I want to do that, it's pretty easy. And you know what? I'm going to throw something in here, because maybe this is a good way to introduce the trick, but I'm going to throw something in here. I'm going to throw a little phantom guy on the side here. I'm going to throw a little phantom. Oops, I wrote him wrong. Pretend he's not here. He's just hanging out. He's just hanging out over there, right? That's not part of the equation, but we're going to leave him there. So let's say I want to do that, right? How do I do that? Well, the first thing I need to do is I need to knock out that C, and we already said if I take C divided by A, that'll tell me how much I would need to knock it out, how much I would need to add this row by, right? So that means I want to take this row and I want to multiply it by negative C over A, right? Then I want to add it in, and that's going to knock out that C term. It's going to turn that C term to 0, right? So let me just do that. Let me just rewrite it that way with that added in there, right? So I've got A, B, I've got my X equals, right? I've got my U. Come on over here. I've got my 1, my 0. But now this next line, I'm going to add the top times negative CA to what we've got here, right? And so obviously in here, well, if I have negative C over A times A plus C, right? You can see that what happens there is the A's cancel out and the C's cancel out, which gives me the 0, right? Which is exactly what I thought. So that's the 0. Then in the D term, we just have D, right? And then minus CB over A, right? So that's just adding those together. We're not going to actually bother figuring out what this guy is right now because these are the unknowns anyway, so we don't really care about those guys at the moment. But we're going to do the same thing to our UV over here. We're going to do that same add, right? So we would take our V and we would add to, we'd subtract from it CU over A. And now while we're at it, I'm going to just go ahead and do the same thing to this identity matrix over here, right? And so I'm going to take my 0, right, and I'm going to add I'm sorry, negative CA times the top. So that's just a negative CA there, right? Because it's a 1, right? So it's just negative CA. And the same thing here, I'm going to add negative CA times this to this guy, which would still just be 1, right? Because there's nothing in there, right? And so that produces now for me, this is called an upper triangular matrix. It produces for me a matrix which has no valid values below the diagonal, right? I've got my 0 in there. My 0 is just kind of sitting there, right? But it's not quite done yet, because while I actually do now know the answer for one of my unknowns, right? I could actually solve for one of my unknowns now if I wanted to, right? I've got this, right? I've got D minus CB over A, and I've got V minus CU over A, right? So if you think about what this meant, right, in terms of the actual equations, I actually do have one straight across equivalence that I could write, right? I could say D minus CB over A y equals V minus CU, CU over A, right? And I could solve that if I wanted to for y. I could just, and that's actually, looks like that, sorry. I could solve that for y by just dividing this over to the other side, right? I just have the D minus CB over A, right? And so I would just have my y equal to this term. So I now know what y actually is, right? But although I can read off the y from this tabular result, right? I can't actually read off what the x is, because the equation on the top still has ax plus by equals u, right? So it turns out we can eliminate this one further, because now that we have a row that's 0 and 1 value here, right? We can just do it the same thing we were doing before to knock out the value above it. Because now that it's got a 0 here, we can use it to eliminate things without touching the other column, right? So if I now take b and I divide b by this value and subtract that, I would finish eliminating, right? I would end up with a0, because this is not going to get touched. And if I just if I take b over this value and add it to b, I end up with the exact same cancellation that we had here. So I'd have a 0, right? And I have d minus cb over a down here. Don't care about the unknowns for the moment. And so then if I come out here and say, okay, do the same thing to it, I have to do that same multiplication. So I have to take, again, b over d minus cb over a. That was the coefficient that we were using, right? Negative that. I have to take that and add it up here. So I would end up with, and it's a little bit ridiculous, right? But I would end up with u minus b over d minus cb over a, right? Times v minus cu over a, right? That's what I would end up with. Again, this term would be the same down here, right? So that's the solve, right? But don't forget, I wanted to do the same thing up to this sort of phantom matrix. So if we keep the phantom matrix going, right, we'd have that negative c over a. Although actually, now that I think about it, that would actually get multiplied up, right? That would actually come up. So what we actually have here is a little more complicated, right? We have 1. And now here is our, I'm a little further, negative b, I almost need, oh, you know what I need? Look at that. That was awesome. All right. So I have to take this and I have to multiply it by that and add it up to the top row, right? So I would have this 1. I would have a plus, because this is 2 negatives, so these are actually going to cancel out there. I would have c over a times b over d minus cb over a, right? I would have negative ca still in the bottom, right? I would have still my 1 down there. And then when I, up in the top here, I would have just this term times the 1 that I'd be subtracting up. So I'd end up with my negative b d minus cb over a, right? Now, the chances that I did all that without making a careless error somewhere are like 0%, right? So there's a 0% chance that that's correct, but there's like a 100% chance that was a reasonable approximation of how Gaussian elimination works mechanically, meaning if you had not done it incorrectly, right? And then what you end up with is just a system of solved equations, right? You know that this equals this, and you know that this, I'm sorry, I should say this times this equals this, and you know that this times this equals that, right? So finally, if you wanted to, you could simplify the whole thing by just dividing the top by A and dividing the bottom by D minus CB over A, right? Because it's free for me to do so. And in fact, probably what I should have done, again, if I was smart, if I was Gauss, because I'm sure Gauss would have done this, but I'm not, when you got down to here, you'd do the divide first. In fact, that's how Gaussian elimination normally works. I overcomplicated things. You could think of, you could ignore this step if you wanted to and say, oh, okay, right here, divide, this guy, divide everything in this row by this, and then it would just be a 1 in there, and that makes things a little simpler. But the reason I didn't do it that way, doing it this way, is because we're working with equations, not numbers. When you're working with numbers, it's free for you to do that divide there because the numbers just do it, whereas it just gets even more complicated if you actually do the divide, right? So anyway, 6 of one, half dozen of the other. You can totally see how that Gaussian elimination works out. And what's kind of cool about it is if you keep the phantom matrix on the other side. Now we haven't finished because we have to divide. We have to divide by A and we have to divide by DCV. But if we were to do that to these two rows, this phantom matrix actually becomes the inverse, which is kind of interesting. And again, I don't actually remember the motivation for why that's actually true. I'm just not sure what the reason is why. It's a neat trick you can do where you can actually solve for inverses while you do it by putting it there. But point being, so if you see how this sort of all works out, that's the Gaussian elimination pattern. That allows us to actually sort of do that solving on matrices when we want to do it. Now, what we would probably want to do is actually do the divide out, finish it here, and just bake it down so that we can actually just not have to even worry about actually solving this ever, right? Because we would just be wanting to produce inverse matrices. But I kind of wanted to show you how it works through for Gaussian elimination anyway. Don't ask me why. I guess now that I think about it, I suppose we probably don't really need to do solutions like this in Handmade Hero. I don't even know. I'm trying to think if we're ever actually going to have to do that. Yeah. I don't know. Point being, I got a little overexcited there, but I wanted to show you how that works, and so that is how that works. And that's a way that you can actually solve arbitrarily large matrices as well. It's just, it turns out to not be particularly good. Once you get up to very kind of like ill-conditioned, very sizable matrices, you usually have to switch to something that's not going to be exact, because Gaussian elimination is like an exact non-iterative scheme. And you typically end up switching to something that is an iterative, like a convergence-based scheme that kind of like converges on the right result rather than trying to solve for a result using what I just did, where you're kind of looking at it like, solving for, you're actually basically doing the mechanics of solving for an equation yourself, right? Solving the actual terms separately. So anyway, unfortunately, we're out of time because I just spent too much time down the math hole. And we didn't quite get to what I wanted to get to, which is this guy, the inverse transpose. Basically, I was trying to lead up to what the inverse is. We'll sort of have to finish that up tomorrow, I guess, and then we can talk about what this is. I told you what the transpose was. We're sort of trying to see what the inverse is. The inverse, now that we've sort of almost got it over here as well, the inverse, like I said, is the thing where if you were to multiply a matrix by its own inverse, it's the thing that gets you that identity back, right? And it's also, if you think about it, the thing that allows you to talk about solving equations that involved whatever that thing was, right? And so if I had some kind of an unknowns thing, like I was talking about ax equals b as a problem, where normally the way we've been doing it is we've been focusing on, we are given x, we are given a, and we're producing b, right? And we've done this a bunch of times now, right? This is the thing that we've basically always been doing. It's the px times the x-axis, py times the y-axis thing. That's basically this. So we've been doing the forward thing. We've been basically doing ax produces b a bunch. What we haven't been doing is given a b and an a, how do you produce the x, right? And so what you could see from this equation is if you had A inverse, if you knew what A inverse was, right, which was what we were building up to there, you could multiply both sides, because remember you can multiply both sides by the same thing. You could multiply both sides by that inverse and you would solve the equation, right? There's the equation in terms of x. So the inverse of something times b is what gives you which x you would use to produce b under that transform. So you can see this quite literally if you had a situation where, let's say, in exactly the sort of thing that we were talking about before, where we have an x-axis, no, how many times am I going to do that? An x-axis and a y-axis, right? We've got them. And typically what we've been doing is we've been saying, okay, here's our actual our coordinate system, and we've got some point that's relative to this axis system, produce the point in this outer axis system, right? And we've been doing that by essentially, if this is A, if this was transform A, we've been producing AP, right? We've been saying P prime equals AP. That's what we've been doing, right? And we've been doing that, we've been writing it out like px times the x-axis plus py times the y-axis, but like I showed earlier in this episode, you can just write it that way as well if you wanted to, right? Well, the inverse thing solves the opposite question. If I was to say, all right, let's say that P was actually not described in this space at all. It was described in this space, right? So it's P prime now. It's this. Given this A, tell me, what is P inside A? I want to map it back into the coordinate system that it was coming out of before, right? I want to do that thing. That is this solve right here, right? That is, instead of AX produces B, that is we have the A, we have the B, right? This is the P prime here, and this is the P. Instead of being given the P and producing the P prime, we want to go the other direction. And that's exactly what that inverse allows us to do. It would allow us to multiply both sides and produce the vector that we actually want, right? So we're not quite there yet. Unfortunately, we ran out of time, largely because my Gaussian elimination is slow. But we'll try to pick it up tomorrow, and I'll pick up where we left off here about how you produce the inverse, and then we can sort of see how we would produce this and why we might care about A inverse transpose. Hopefully you can see why you would already care about A inverse up here, but we have another thing to talk about, which is when A inverse equals A transpose, which is a separate thing as well, but that's not the case here anyway. All right. That is the end of the math hole for today. Sorry I sprung it on you. I would have prepared people had I known I was going down the math hole. I didn't. But it is time for Q&A. It is time for Q&A. If anyone would like to ask questions, as long as that question is is not why are we in the math hole, I can probably answer it. I like the fact that this thing has been in here the whole time, right? It's been doing that. Multitasking. For inverting 2x2 matrices, a simple cofactor equation is quite efficient. A simple cofactor equation. Okay, you have a link there, but I can't really read the thing now. Mr. Fourth Dimension says all the steps in elimination can be represented as a matrix. Starting with M and multiply by all those matrices, you get the identity. So those matrices multiplied together are the inverse. Multiplying them all by the identity gives you the inverse. Is that the trick you're alluding to? Yeah, you know what? I think that was. It's been so long since I've done any linear algebra. I mean, like, crazy long. It's easy for me to forget, but I think you might be right about that. I think that is exactly how you do it. So if you think about what I was doing here, right, let's take this very first step. And thank you, Mr. Fourth Dimension, for saying that, because I believe that is exactly what I would have had to go look up, and now I don't have to look at it. So the trick here, right, is if you imagine having this guy, right? So I start with this dude right here. And I wanted to do this operation on it, right? I wanted to do this operation where I did negative CA times the top row and added it to the bottom row. Well, actually, I could do that I could create a matrix that actually did exactly that, right? And the matrix that does exactly that, is just the one that produces this result, right? So if I take that AB, right, I'm going to do it this way, right? If I take that AB, I need whatever the result is here to still produce A, and there's only one way to do that, right? Which would be 1, 0, right? That would still produce A here, which is what I need, right? And in terms of what would produce B in this slot, I would need... Wait, how does this work again? What am I missing here? Did I do that right? 1, 0, because this has to be the negative CA version. Wait a minute. Because this needs to be A, this still needs to be B, this needs to produce 0, and this needs to produce D minus CB over A. Or rather, negative CA times B. So that negative CA has to yeah, I guess it would have to come in. I'm not sure. You know what? I'm gonna hold off on that. It's been too long since I've done this. I'm just totally doing this wrong because I'm trying to think of how you actually do the matrix that produces that elimination, and it seems like you would still have to end up, in order to produce AB on that row, you still have to produce you'd still have to produce a 0, a 1, 0 at the top, which doesn't seem right to me. Because once you do this guy, right, you need to produce a different vector here, right? Yeah. I'm not sure I remember how to do that. Let's think about it for a second. Let's not give up quite so easily. Because yeah, you should be able to produce a series of matrices that do the permutations on this matrix that eliminate it eventually, but I don't remember what exactly they are, because it seems tricky to produce this. So if I just wanted to add negative CA, right, if I just wanted to add negative CA to this row, right, I would have to produce, I guess you could almost imagine as producing negative C here, right? And so this, yeah, I don't know. I don't know how I would do that. I do not know how I would do that in a way that still produces the A there. Yeah, that's too much for my math brain right now. Robot Chocolate Dino, to find the inverse matrix, couldn't we just rotate by the negative angle and scale by 1 over the amount that we scaled by originally? Yes, that is how you would construct the inverse matrix. And oftentimes you will do that in graphics because it's easier than inverting the matrix potentially, depending on the circumstances. But I wanted to talk about it a little more generally because you don't always know where your matrix came from, right? That's only if you happen to know. And so to be more explicit about what happens there, right? If you know that your matrix, right, happens to be a scale times a rotation, and you know what that scale and that rotation was, right, then instead of computing A inverse, right, you can instead just go, oh, well, if I wanted to compute A inverse, I could instead just take the inverse of SR, right? And this is a little more than I probably wanted to get into, but basically that's the same as this. And if you look at what these guys are, right, the inverse rotation and the inverse scale matrices are exactly what you just said. If I have a scale matrix, it looks like this, right? It's got an X scale and a Y scale and nothing else in it. It's a diagonal matrix that looks like that, right? And hey, lo and behold, what would produce, right? What would produce the identity? So if this is my S, what's my S inverse, right? Well, no surprise there, right? It's 1 over X, because 1 over X times X equals 1, right? And 1 over Y, with zeros on the thing, that would produce the identity, right? So that's exactly what you were just suggesting or doing, is that right there. And the R inverse is whatever would rotate you back to where you were. It's a little bit harder to show why that works compared with this one, but if you think about it, it's actually not too difficult. We might be able to kind of show how that works here. So let's say we have that rotation, and like I said, that's just those rotation matrices, like I said before, are just putting in the x-axis and the y-axis, right? So if I have the x-axis and the y-axis, I have xx and xy and yx and yy. If I have that in my rotation matrix, and I want to know, what times that is going to equal to, is going to be equal to the identity, then what I'm looking for, right, is I'm looking for a vector here that when dotted with these two things, when dotted with x, xx, yx, and when dotted with xy, yy produces 1 and 0, right? And so what you can kind of see here, if you take a look at what's happening, right, is you're trying to produce a vector here, which is essentially the same as the vector here, right? Because we know that if I have two vectors, we know that all of these are unit length. If it's just a rotation, right, then we know that the x-axis length is 1 and the y-axis length is 1, right? So what we know is that if we were to dot the x-axis with itself, we would get 1. And if we were to dot the y-axis with itself, we'd also get 1, right? We also know they're perpendicular, so if we were to dot the y-axis with the x-axis, we would get 0, right? Similarly, it's symmetric, right? So the dot product is commutative that way, so we get that, right? So what we're asking for here is, okay, what would the thing that would multiply with these guys and produce a 1, right? Well, we sort of know that if we just were to take this guy, we basically know if we were to take this guy and dot him with himself, we would get a 1, right? And if we were to take this guy and dot him with the other vector, we would get a 0, right? So it turns out that when you actually produce the inverse for R, you literally get exactly what its transpose was, right? So you can actually see here, like if I finish it out, xy, yy. You can actually see that all this is it's the same matrix but with these two guys flipped. And then when you do that math out, you get x squared. You get x squared plus y squared. You get xx squared plus yx squared, which equals 1, and you get x y squared plus yy squared, which also equals 1 there, right? And the other two were 0. And again, the only reason that that's true is because all of these things were also true, so we know those relationships between the scalars. But yeah, we should really go into that in more detail if you really wanted to be a little more explicit about it, because it's hard to see why changing, it's kind of hard to see why that actually works out the way that it does. But trying to think if there's another way I could sort of show you what was happening there. Because this vector is not the x-axis, right? This is like half the x-axis, half the y-axis, right? If you think about it, it's the x components of both of them. So it's just a little bit it's a little bit confusing as to why that works out the way that it does, right? So yeah, but we can go into that in a little more detail. Maybe we should do a section on like rotation matrices and why they work that way. But that's how that R inverse works, and that is just the opposite rotation, right? So in 2D, you can almost, I mean, one way to think about this is, do you remember the perp operator, right? Where we did the sort of perpendiculars? One way to think about it is that's sort of what's going on here, right? Remember what the perp was. So if I have a vector xy, and that represents something, right? So this is my vector, right? Here's my vector xy. If I want to produce the perp to that, right, what we did is we did negative y over an x, right? We swapped the order that they were in, right? And so you can kind of think of the same sort of thing as yeah, no, this is not a very good explanation either. let's hold off on this. I'll think about this a little bit to think about how I could more easily explain why this works out for transposing, right? Because I want to be able to show that a little bit better than I showed it. I don't think I did a very good job there. And so if you have, you know, an x-axis and a y-axis in the columns, and then you go ahead and want to produce that that identity matrix from that, and you end up with the x-axis like in the rows like that, it's just kind of a little confusing to show it. So I guess, you know, all right. So this is a little cheesy, but here's one way I could show it, by doing it the opposite order, right? So let's suppose I have x, which is our x-axis that we're using, and I have y, which is our y-axis, right? So let's suppose I just drew it the other way. Here's our rotation matrix, right? And we have the x-axis as a column, and we have the y-axis as a column here. This is a much easier way to show it. So I apologize for not having an easy way to show it the other way, but it's a little bit more confusing, right? So if I want to construct the inverse here, I've got one. Yeah, this is much easier. If I put the inverse on the left side, even though they're equivalent, putting them there makes it much easier to show this, right? So what did I say? I said x transpose x equals 1. I said x transpose y equals 0. I said y transpose y equals 1, right? Why is that true? Well, it's true because any unit vector dotted with itself is 1, and any unit vector dotted with a perpendicular is 0. We covered that, you know, in previous episodes. So we know that those are true, right? So we want the x-axis dotted with something to produce 1. Well, obviously, the x-axis dotted with its own self is 1. And if I did the x-axis dotted with the y-axis, I'd get 0, right? That's just what I wrote over here exactly, right? That's what I'd get. And similarly, putting the y-axis in here does the exact same thing. X-axis dotted with the y is 0. Y-axis dotted with the y is 1, right? So if you put them in this order, you can see really clearly when you do the dot products why they come out to be the things they are. Doing it the other order is harder to see because you're in the column picture of the matrix, which is just harder to, you have to then write it broken out, and we could add it up the column way. So I think the way I'd have to do that was, remember up here where I sort of broke things out in that other way? I was like, here's the other way, here's the other way we wrote it. I think you'd have to actually do it that way, and then you could see why it would work. But that's, it's much easier to show the dot product version because that was just, as you saw from when I just did that, it's a really straightforward thing. You can just read it directly out. Let's see. Ollie Holly, I remember doing this by putting the identity besides the original matrix and performing each step to each. Yeah, that's what I did, and that actually does produce it, but I just don't remember why. I don't remember the explanation as to why that actually works, right? Oh wait, duh. I know why. Yeah, it's just been a long time. I'm sorry, I'm really rusty at my linear algebra. I totally know why. It's very simple. If I have A, right, as a matrix, let's say I did AI equals A, right? So I already said that I is the multiplicative identity, right? This is the multiplicative identity. So I know that A times the identity matrix equals A. Right? So I just have A, B, C, D. There's my A matrix. I have 1, 0, 0, 1, and I have that equals A, B, C, D. I don't know why I couldn't think of this. It was like, yeah, it's just been too long. One of the nice things about the stream is I have to remember all my math, which is good. I mean, it's good to keep it active in the brain, right? So this times this equals this. We know that's true. We already said that's exactly what that is. So A times the identity equals A. So then you just do the elimination here, right? You do the Gaussian elimination until this equals the identity, right? Like I was doing above. You knock out the terms and you divide. Once you are done with that, you will end up with the identity, right? Some matrix here, right, equals the identity on the other side, right? Because if you eliminated the terms here, and this is the same thing, you would eliminate the terms here. What is this, right? What is that, that matrix that you would end up with sort of in the middle, right? Oh wait, no, that doesn't quite work. Because you'll end up with the matrix here, but why would it still do the inversion? All right, never mind. I'm still not sure about it. Because then you don't quite end up with the right thing, right? You don't quite end up with the right thing because you'll end up with I something equals I if you do it all to both sides, which in theory means shouldn't this have to also be I? That's a little confusing. This is confusing. You know what I'm going to say? Math is hard. Let's go shopping. I'm going to have to study up. I basically have to study up a why that, because now that I think about it, yeah. So this is just hard. Because I feel like you should be able to do the elimination with an identity matrix, and then the identity matrix comes out to be the inverse, which should leave you with A inverse equals I, right? You should end up being able to do some elimination that way, where you end up with swapping the two. Darn it, I thought I had it, don't have it. If you had a matrix such as int 2, 2, with the example of A, B, C, D as the variables in place, couldn't you just swap A and D and make C and B negative? You mean making the inverse? Well, you can verify whether you can or not pretty easily, right? So what you just said was, I'll copy down, swap A and D. So there's swapped A and D, and make C and B negative. So there you go. So what happens if you multiply this out? Well, if I do the dot product, I would get AD minus CB. So I mean, you can already see it's not the identity, right? Because this should be equal to 1, and it's not, right? Meeblo, I understood none of today's episode. Would you recommend that I rewatch it, or do you think all may become clear tomorrow? I don't know. It's fairly complicated stuff. So I would say watch tomorrow's episode and then possibly rewatch today's. I will try to go find where the trick is for this just so we can finish that up. And then we'll go implement something that actually does the inverse. So Naysayer88 says, here is the explanation for computing the inverse. If you write A and then I next to each other, okay, and then apply, which is what I was sort of doing or trying to do there, but okay. If you write A and I next to each other and apply a bunch of operations, you're computing T3, T2, T1A, and T3, T2, T1I. Because you ended up at the identity T3, T2, T1A equals I. So T3, T2, T1 equals A inverse. Therefore T, so that's, So that's interesting. I guess I'm not, I feel like there should be an equation there, but maybe there isn't. So that was John Blow saying that. What he was saying is, well, don't worry about the fact that what you're about to do here, don't worry about the fact that you can't do it as an equation. Just write A and I next to each other anyway. And he said, when you apply a bunch of things to both of them, so if I have A and I have I, when I apply a bunch of things to both of them, right, then whatever the steps are, he was calling them T1, T2, T3, whatever the steps are that reduce A, and this actually makes some sense, whatever the steps are that reduce A to the identity, right, because if we do all these steps and we make A the identity, right, then obviously they must have been equal to A inverse, because they produce the identity, right? So whatever this is times this, if we ended up with the identity, right, then this must have been A inverse. So if I applied the same steps to the identity, I would just get the inverse, right? Because there is no anything else there. It would just be T1, T2, T3. So that's why that trick works, right? That's why you can Gaussian eliminate this next to this, right? That's why you can do the Gaussian elimination steps. As long as you do the same steps to this, you end up with basically the matrix, you end up with the identity matrix turning into the inverse when this turns into the identity, right? So when this becomes I, when A becomes I becomes A inverse. And that's a pretty good way to explain it, right? Whatever the steps are that you applied to A, they must have been the inverse if they drove A to the identity. And so, you know, if you wanted to apply those to an identity matrix, you would end up with just the inverse. So that's a pretty good way of thinking about it. Thank you, John. So I guess we're done actually with the trick. We can actually go back here. This is crazy how much math. Look at this. Look at that. This was all, where did we start? Where did we start on today? It's crazy, right? It was like here or something. That's awesome. I love zooming out on the blackboard. That's great. So yeah. Okay, so we didn't quite get there, but we almost got there. And thanks to John, we also have an explanation of why the thing I was showing there would have worked, or should work, right? Which we did not have before. All right, so what we'll have to do is we'll have to postpone for day 102. We'll just leave it right here. We'll have to do inverse transpose. Oops. Inverse transpose. A inverse transpose, right? Because we still have to talk about that now that we sort of know what this is. Although I'll try to do a little bit better job quickly explaining a little bit more of that, since we got a little bit bogged down today. I'll try to do a little bit more concise job of talking about A inverse. We already know what the transpose is, and then we can talk about why normals are transformed by A inverse transpose, not A. And I sort of drew out why that was on the previous one. Okay. I will go ahead and save the mischief blackboard. Close that down. And this. Okay, thank you everyone for joining me for another episode of Handmade Hero. It's been a pleasure today going down the math hole with you. It's always good to have other people in the math hole. As always, if you would like to follow along at home, you can pre-order the game on handmadehero.org. It comes with a source code, so if you want to play around with the source code, that's a good way to do that. You can also subscribe to the Patreon if you want to support the video series. We've got one up there. We also have the forums that you can ask questions and get ports to Linux and Mac of the code base so that you don't have to do that yourself if you want to follow along on other platforms. And similarly, it's got annotated episode guide up there if you want to catch up with previous episodes. We also have a tweet bot that tweets the schedule, so if you want to catch up with the episodes as they are aired, you can always use the tweet bot to kind of figure out when those are happening. So I highly recommend checking that out if you're trying to catch the series live. That is about it for today. I will be back here again at 5 p.m. tomorrow. If you would like to see the conclusion of how to do our normal transforms so that our normal maps will work properly, you can go ahead and come back tomorrow, 5 p.m. Pacific Standard Time, same place here on Twitch, and we will do that. Hope to see everyone tomorrow, and thanks for tuning in. Take it easy, everyone.